You have probably seen a compass needle settle, almost calmly, into the same direction each time, even when you rotate the compass in your hand. A common assumption is that the needle is somehow pointing at the North Star, or that it is guided by north as a location on a map. That assumption is understandable, but it is incomplete, because a compass does not respond to a star or to geography in that simple way. What is the needle actually aligning with? Why does it work in daylight, indoors, and under clouds? And why does a compass sometimes seem a little off from true north? This can be explained clearly once the role of Earth's magnetic field is made concrete. The key misconception is that a compass points to the geographic North Pole. In reality, a standard compass aligns with Earth's magnetic field, which is produced by moving electrical charges in Earth's outer core. Deep beneath the surface, molten iron and nickel flow in complex patterns. Because moving conductive fluids create electric currents, and electric currents create magnetic fields, Earth behaves like a giant magnet. The magnetic field extends outward into space, and at the surface, it has a direction at every point, like invisible lines showing which way a tiny magnet would prefer to align. A compass needle is itself a small magnet. It is usually a lightweight piece of magnetized metal, balanced on a low-friction pivot. Like any magnet, it has a north-seeking end and a south-seeking end. When you place it in Earth's magnetic field, the needle experiences a torque, a turning force, that rotates it until it aligns with the field. It stops when the magnetic forces are balanced, and the needle is as aligned as it can be. So the compass does not know where north is. It does not read a map. It simply rotates to match the local direction of the magnetic field. The direction your compass indicates is called magnetic north, meaning the direction toward which the field points along the surface. Magnetic north is not exactly the same as true north, which is the direction toward Earth's rotational axis. The difference between them is called magnetic declination. Declination varies by location and changes slowly over time because Earth's magnetic field is not perfectly stable. This explains why a compass can be slightly inaccurate for precise navigation unless you account for declination. In some regions, the difference is small. In others, it can be large enough to matter. Many maps include declination information, and some compasses allow you to set it so the needle points closer to true north for that area. A compass can also be disturbed by nearby magnetic materials or electrical devices. A steel table, a phone speaker, a car body, or even power lines can distort the local magnetic field. When that happens, the needle still follows the strongest field it detects, but that field may be partly produced by nearby objects rather than Earth. That is why good compass use involves stepping away from metal and electronics. There is also an important edge case. Near the magnetic poles, the magnetic field lines tilt steeply into the ground. This means the needle can dip, and the horizontal direction becomes less stable. Some compasses are balanced differently for different hemispheres to reduce this problem. In extreme high latitude areas, traditional compasses become harder to use reliably. The system exists because Earth's internal physics naturally generates a magnetic field, and small magnets naturally align with it. The compass is essentially a simple instrument that turns a planet-scale field into a usable direction. In everyday life, understanding this helps explain why compasses can disagree with maps, why they can be fooled by nearby metal, and why calibration matters for accurate travel. If you have other navigation or always works tools you want explained with the same calm approach, you can suggest them. And if you want more of these explanations over time, you can subscribe. Thanks for watching.